Holston is obviously super popular in a lot of olympiad settings. Like you have a lot of problems in Hall's theorem disguised as other kind of combinatorial problems or even number theory problems at times. So so usually what people do is you introduce um through like Hall's theorem problem, but what I'm going to do is slightly technical, but not very technical. So I'm gonna introduce a few definitions. Like they're very simple, so don't get scared at all. So the first definition, so first of all, what a matching is. So matching is nothing but if you have a graph, so matching is essentially pairing the vertices of a graph. So the blue lines, which were originally edges in the graph, G, are is a matching. Now, what we care about is matchings which have a larger size because making matchings of smaller sizes is not as complicated. You can just make anything like you can just make a matching of size 1 with one edge, right? So usually we want to maximize the number of matchings. Like, do you think this graph has a bigger matching? It does not, right? Because you have 5 vertices and it can't have like a matching which has 3 edges because obviously you would need 6 vertices for that. So what is a perfect matching now? So again, you have a graph and notice that, wait, this is gonna have perfect matching. But it does not. Okay, let's say add another edge. So yeah, you can connect this edge and these 2 edges. Now all the vertices are covered by this matching. So that is what is called a perfect matching. To define it slightly more formally, say you have a bipartite graph with x and y. So essentially, every vertex in X is saturated in a perfect matching. And saturated essentially means that the edges touch the vertex, right? Is that clear to everyone?
Yeah. Okay.
Okay. If anything is like not clear, please speak up. Like it's hard to maneuver the chat and everything. So yeah, speaking up would be great. Now let's look at a few graphs and try to like find good like matchings with no, lots of edges. Like how do you do this? So okay, let's label them V1, V2, V3, V4, V5. So could some of you suggest a matching for this graph? Like any matching. Like okay, V7 as well. Like this could be a matching, but this is not that great. So you could possibly have a better matching, like the red one, which has 3 edges instead of 2. And that in fact will be the maximum because you can't have 4 edges. So what really is the difference between the maximal matching of a graph and any other matching? So let's figure that out. So first, like, do you have any guesses on like just look at the structure and try to guess what's going on? What's the difference between these two um matchings? Anyone? Okay, so let's just start with one vertex, say V3, and let's travel along. Let's pick matching, say the blue matching, right? Now, let's from V3 we can go to V7, and from V7 we can go to V1, then V1 to V4. Now, V3, V7, V1, V4 is a path where we're looking at the blue matching, by the way, and V7, V1 is blue. Um, yeah, and these are not colored. But if you can notice that you can just swap the coloring. Like you could just color these two blue and remove this color, and you would have a larger matching because initially you had one edge, but now you have two edges, and this works. So if you have a path like like, like a really long path, at the last and at the end you have like this is like this vertex is not saturated. Like for example, here V3 is not saturated and V4 is not saturated. This vertex is also not saturated. This means these two edges are not colored. Then what you can do is you can simply get a breaker matching by like flipping the coloring. Is that clear?
I just joined. Can I know like what was happening till then?
Yeah, I'll just summarize really quick. So we are talking about matchings. So matchings is nothing but if you have a graph, you are pairing the vertices between two, like you're essentially pairing the vertices. And what a perfect matching is that if you essentially say you have a bipartite graph where you have subsets x and y, every vertex of x is saturated as in like has an edge essentially in the matching, like to some
So it's
like
saturated
vertex
if it
in
has
there.
a partner.
Yep, exactly.
Sajal,
Okay.
does that mean that everyone has a partner?
Everyone in x,
Can you repeat?
everyone in x has a part. Like y did not have like it's a mapping like you could have that like x has for example uh 10 vertices and y has 15, then obviously like um if you create a matching you won't have anything that like covers all the vertices of y, right?
Yes.
But by definition, like we are considering the mapping from x to y, and if all the vertices of x are like occupied, then it is still considered a perfect match.
It is like a function, how we made surjective and kind of thing.
Yep, exactly.
Okay.
It's not really subjective, in fact, quite the opposite almost.
Injective.
Yeah, it's an inject like matching by definition is an injective function.
Okay.
So what we're trying to do is we consider two matchings in this graph, and and yes, so you have one blue matching and one red matching. So we're trying to analyze what's the difference between a blue matching which has two edges and a red matching which has three edges. Like obviously the red one is the maximal possible matching because it saturates six vertices out of seven. You can't do more than that. So what we found out is if you um like start off with V3 and like consider this part V3, V7, V1, V4. So V7 and V1 are connected by a blue edge, while these are not colored. Notice, don't confuse it with the red edges. These are two separate matchings. So technically, these two are not colored. But what you could do is, instead of considering this edge, you could just remove this blue edge and consider V3, V7 as the blue edge and V1, V4 as the blue edge, and you would have a larger matching, right?
Yeah, so it improves the matching.
Exactly. So essentially, if you have any path like this, like a very long path, and you have like these two edges are not colored while these are alternatively, then you can just flip the coloring and get a better matching. So such a path is called an augmenting path, where you have where the endpoints of the path are not saturated, right? So obviously, um, we want to find perfect matchings, right? We want to find matchings with more edges. Now, obviously, a matching, if it's maximal, then you won't have an augmenting path, right? But is the opposite true as well? Like, like if is it an if and only if condition? Like if you have no augmenting path, then essentially you have a perfect matching. So we had a weak condition that um wait. But now we want to think of the like stronger sort of a stronger I don't know extension that if you have no augmenting paths, essentially you can characterize perfect matchings with it having no augmenting paths. So can you do that? Is my question.
But if you have a perfect matching which has an augmenting path, then it can't be a perfect matching. So
Yes.
suppose you had the maximal matching.
Okay. Let's consider it to be M.
Okay, then if there exists an augmenting path, then you can always improve it.
Yep.
So
Exactly.
that would mean that M is not the maximal matching, which is contradictory.
Yes. But my point is, um, if you have a matching which has no augmenting paths, is it necessarily a maximal matching?
It could be that no point is connected with each other. So,
So there are no point is connected with each other.
sorry.
I
Oops.
don't understand it what exactly you mean. By the way, another definition, just in case it's not that important, but for example, like we considered a path which is alternating like a vertical, like edges with one's in the matching and one's not in the matching. Such a path is called an alternating path. Just one definition you can just maybe keep in your mind, forget about it.
So an augmenting path is an alternating path.
Yes, which can be improved. Okay, so turns out this is actually true, that if you have any matching that doesn't have an augmenting path, it's maximal. So it's a really surprising result. And if you know what Hall's theorem is, then this probably sounds familiar, where a very sort of obvious condition which needs to be true for a perfect matching is also it also characterizes perfect matchings in general. So there's a really common theme in matchings and everything, where a weak condition can be translated into a much stronger condition. Anyway, so okay, before we prove this, let's sort of analyze what's going on when you have two matchings in a graph. Like, let's just consider a random graph. We'll label them later. So, okay, let's consider eight edges. Eight vertices. Um, let's just draw random edges. That looks good. Yeah. So yeah, suggest me like any two matchings. Possibly says like okay, let's just find a perfect matching here first. Like, could you suggest one perfect matching in this? Does it even have one? If it doesn't, then I have to add a few more edges. So please check it out. Um, wait. Yeah, it does. Okay.
I
Like,
don't
okay.
think it has a perfect matching.
I think I saw one. Yeah, I saw one. Find it.
Ah. Okay, so V1, V2,
Sure.
V3, V7,
I'm sorry.
V6, V4, and V8, V5.
V3, V7, V6, V4, V5. Exactly. That is the one I saw. Okay, so there's a perfect matching. And now let's consider a matching which is not perfect, like a much worse. Swap the color. Okay, let's take these. Like we can really consider any matching, like say V1, V3, V8, V6. It's like a much worse matching. Okay, V7, V6. Yeah. So what's really happening?
Okay, here you can have an augmenting path V3, V7, V6, V4.
Yep. In like the blue matching, you have an implementing path. Okay, now if we remove the other edges, like they're not very important right now, right? Like the black edges are not that important. So let's analyze the structure of the graph when you remove them. So, okay, how do you take a screenshot and paste it? Is there a better way to do it? Damn, I'm such a boomer. Like, can I not do this? I can't? Okay. Anyways, let's just remove the black edges. Like, the edges were not part of the match. So what do we see here? What is the structure of the graph?
Okay, you either have strings or lines.
Yeah, it's a path, right?
Right.
So, okay, let's just analyze another graph. 4, 5, 6, 8. So this time I somehow need cycles on this because else it's not complicated enough for our interest. Or maybe cycles don't exist, who knows? I like cycles though. Okay, so what could be a matching here? Um, wait, is that good? No, it's not. This is fine. Yeah, this is a perfect matching. And let's consider worst matching.
There does exist another perfect matching.
Yeah, okay, that's fine. I'm trying to construct. I'm just trying to like make things a bit more interesting. I'm trying to find a like a matching which is not necessarily maximal, but sort of makes an interesting structure when we delete the blue edges. Hmm. Okay. I'll just add another edge. Like, why not? I decide the rules afterward. Haha. Wait, no, this is not a good enough edge. Oh, this is so sad. Can't make a graph. Um, okay, perfect. Let's add this edge. Okay, now we can consider this matching. Um, yeah. Oh, then this is a perfect matching. That's not nice. Anyways, let's just ignore this edge. Like, this is also a matching, right? The green one is also a matching. Now, what happens when you move the blue edges? Is this a path this time?
Okay, now you have lines and cycles.
You have a cycle, and it's an okay. The cycle is even, right? It has four vertices. So first of all, my question is, okay? So you do have cycles, right? And if you have cycles, can you have odd cycles? Because it's possible to have odd cycles.
No, because then you would have two edges of the same color on one vertex.
Exactly. So you don't have odd cycles. So we found out that you can have paths, you can have even cycles. Now it turns out it's only like a union of even cycles and paths. Like if you remove the other exterior edges instead of the two matchings. So this operation we did, like if we consider one of the matchings to be M1 and the other matching to be M2, it's called the symmetric difference of M1 and M2. And you often symbolize it with delta. So we are taking the symmetric difference of these two matchings, so the blue, like the blue and red matching here and the red and green matching here. Now we want to prove that it's only a union of even cycles and paths. So any ideas for that? Like a graph that contradicts such like our claim is probably this, like the Ursa Major graph. I'm so creative with the names. Oh my God.
Okay, if you ever have a path which has a cycle in between, then you would have a vertex with three uh, of these coming out, three edges, and then
Yes,
two of them must be of the same color.
yes, exactly. So that's not possible, right? So yes, it's fairly simple to prove that it's just a union of paths and even cycles. So we have some structural understanding of when you have two matchings. Now let's get back to our augmenting path claim. So, okay. So I will give you a few minutes to try the problem. Like those who joined, um, wait, let me just check the chat. Okay. So essentially, we want to prove that if you have a perfect matching, such that it has no augmenting path, then it is the maximal matching. Like it is the maximal like perfect matching. Let's just call the matching like M, the one which has no augmenting path and yet is somehow not the maximal matching. And suppose for the sake of contradiction, you have a matching like, okay, let's consider it to be M1, and you have a matching M2, which actually has like mod M2 is greater than mod M, right?
Okay, then suppose M2 is the maximal matching.
Yeah,
Then you take the difference of all of them, you remove all the other edges.
yeah, you take the symmetric difference of these two.
So now your thing is only a bunch of cycles, even cycles and paths.
Yep,
Even cycles don't give you anything extra, so you can just remove them for now. They don't give
exactly.
you.
Just ignore them.
And since you have no augmenting parts, you must all have even parts with same
Yep.
number of these
Okay.
each other. So then that means that if you have even parts, that means both the matchings have the same number of edges.
It has to be the same,
Oh, but you
right?
can have ones with M1 greater than M. Oh no, yeah, that's
Yeah, exactly. That's it. So does everyone get how the proof works? So I will just summarize it. So the idea is to take the symmetric difference because you get a lot of like information on the structure of the matchings. And we know from the proof above that it has to be a union of paths and even cycles. Now, even cycles are kind of boring. They don't really give you that much information. Like, obviously, they have to be like they will have equal number of edges of the two matchings, right? So you consider the paths, and you know that we assume that we have no augmenting paths. So clearly, you can't have an odd path because if you did, sorry, oh, is that an even path? Oh wait, that is even. Yeah, essentially, if you had an odd path with like odd number of edges, then you could just swap the coloring of blue, right? So you can ignore them. So now you consider even like paths, but even paths must always have equal number of blue and green edges. Else you will have like two blue edges or green edges coinciding, which is not possible. So indeed, um, no augmenting path in a perfect matching implies it's maximal matching. Is that clear to everyone?
Yeah.
Great. Okay, now we have good structural understanding of how matchings work, how perfect matchings work. And again, we're going to introduce a sort of a weak condition and sort of extend it to be very strong later on. So also, so before you know what Hall's theorem is, let's just consider a bipartite graph. A bipartite graph, just in case you don't know what it is, it essentially you can divide it into two sets of vertices, say x and y, such that these have no vertices among each other. Like two vertices xi and xj will have no vertices in common, like no edges in common, and yi and yj will not have any edges in common. You will only have edges across these two sets. So let's look at one vertex. So we want to find the number of not the number, I'm sorry. if a perfect matching, like, yes, we want to find perfect matches. So what's the requirement for like one vertex to have a perfect matching? It needs an edge, right? So it's an obvious condition that degree of a vertex in X should be greater than equals to 1. But okay, let's extend it a bit. Let's consider this subset. These two vertices, X1 and X2. Now, what's the requirement for this subset of X to have a matching in Y?
Degree should be greater than equal to 2.
Um, Degree should be greater than equals to, as in the like the entire like of the entire subset.
Like the like x1 matches the number of like vertices and x2 matches. So that union should be like greater than equal to like the neighborhood, I mean.
But then this can happen, no? Like this union has like degree greater than equals to, but then it doesn't have a perfect match, right? So you actually need both of these conditions together. And you can keep on extending this.
But doesn't the first condition just imply the second?
It does. Wait, does it necessarily wait? Yeah, it does. Okay. But okay, it does imply. But if you have larger subsets, this is not necessarily true. Because you could have like one like lots of vertices going to one vertex. So yeah. So essentially we can formalize it like this. Like if you have some subset S of X, then mod S um will be less than equal. Like the neighborhood of S will be like has to be like greater than equals the cardinal number of S. That's like it has to be true, else we can find the contradiction easily as we saw, right? But now it turns out that this is also sufficient to find a perfect matching. Like the simple condition, if this is always true, like across all subsets, you will have a perfect matching for sure. And this sounds very intuitive, but still, it's a very weak condition. It still gives you like a lot of profit. And now we're going to try to prove it. So how exactly do you think we should approach proving this? Like previously also we had a weak condition, then we translated it into a much stronger condition. You have a perfect matching here as well. You can check that Hall's condition is true.
So the condition only gives you a perfect matching between S and NS generally, unless you have some of the vertices in S, their edges clump to only less number of ones there in NS, but and you have another vertex in S that uh, is paired up with more number of vertices in NS. But if that is the case, then you can just remove that vertex because you need to take every subset in the graph, and then you will always have a perfect match.
How exactly are you constructing this?
So, suppose you just have the set S and N of S,
Okay.
and you're given this condition.
Okay, let's
So,
just consider this. Like this is S and this is N of S.
okay, so you're given this condition, but that implies a perfect matching if and only if you have no. This implies a perfect matching unless you have one vertex in S kind of uh, branches out to more vertices in N of S, and then
Okay.
you have another vertex in maybe in S, with you have a bunch of vertices in S that go to on just one or couple less. Like you can take the name subsets of S itself, but since you're and that will not give you a perfect matching.
Okay.
But since you're taking every subset, there will exist one subset where you're just taking where you are completely ignoring the one the edges, the vertices which are clumping onto one vertex in NS.
Yes, I get the intuition, but is that formal though? It's not formal enough. Like, yes, exactly. That's like perfect intuition. Like that's exactly what's going on. And the idea is in fact quite similar. Like the idea of the group is quite similar. Yeah.
We could induct on the fact that perhaps I'm not sure if it's we should induct on like the number of vertices, but like we could induct on the fact that this holds, and then we say that since a perfect matching does not exist for that element or element of the list, then this Hall's criterion is violated of some sort.
Yeah, so induction is sort of weird. I think you can induct. Like there's an induction proof, but that's fine. But like okay, you essentially want to prove it with like contradiction essentially. So are you saying like you want to assume that okay, like you have a like wait, so yeah, so
We
essentially you
can
want to like
probably,
go on.
yeah, we can probably consider like maximal matching and say like there is a point P that is not in the maximal matching.
Okay. Okay, let's just construct a graph together. That makes things lot easier for everyone. Um, yeah. So which ones do I connect? Wait. So we assume that Hall's condition holds in this thing, right? Okay, and hopefully this graph will. Okay, let's not make this very boring. Let's make the graph a bit interesting. This should be interesting enough. Yeah. Okay. So let's consider a matching. Okay, Aritra, you can. And so you wanted to like you assume that you have a matching. So it's like you have maximal matching that doesn't saturate one vertex in X. Suppose it's this one, right?
Uh, so what we wanna do is like we can consider another vertex A1, let's say,
Okay.
on X only.
Okay.
And like if the vertex, like the vertex P has like a edge not outside it, so because then that would be maximal matching. So that has a like edge that is on the like B1 to BJ problem, you can say.
Okay.
And
So
if
these are wait. So these vertices are BIs and these are AIs, right?
yeah,
Okay. Go on.
so I am saying like say P matches to like some BJ.
P,
Yeah,
like this one.
yeah, like the P can't match to something that is not in BI, because like that will be the maximum matching then. And we consider
Oh,
like,
okay. So yeah, its neighborhood is already off.
yeah, its neighborhood is already occupied by the AIs thing.
Well, let's
So
just draw that matching. Like let's just draw a sample matching to like make things simpler, right? This one, right?
yeah.
Okay.
So what we want to do is like say that if A1 the vertex has some matching that is not in BIs, then we can probably shift the
AI
place of
hasn't
A1 and P. Uh,
okay. So I don't understand what exactly you're saying. So A1 has a
no,
matching.
I am trying to say that like say that A1 to AI are already matched, like that's a
Yeah.
maximal matching.
Yep. These are matched.
So
Yep.
say like A1 has a maximal matching that is not in BI, and A1 has a like H2 like some uh, vertex on Y that is not in BIs.
Wait, what are BIs? BIs, how are we
BIs
defining
are the
BI?
part of the maximal matching, like AIs and BIs are the vertices that are maximal matching.
Ah, okay. Sure. So you
Wait,
were
what was
considering
BI again?
like
I didn't get that definition.
so okay. So why since okay, let's make it clear. Mod Y can be greater than mod X, right?
Yes.
Now the matching set like the matching maps to some subset Y dash, and I think he's considering BIs to be like those in Y dash essentially.
And you're assuming not everything in X is are AIs.
No, not everything in X. Like P is not in AI because like then
Yeah,
if
that's
P
the
is in
only
AI, then
thing.
will be like maximal matching. Like that's what we want to prove that it can't happen only.
Yeah. So AIs are just these, right?
Okay, so you're assuming that one is not in the maximum matching, and then you're trying to disprove. Okay.
Yeah. So like if all the matchings that P has to be in like the BIs, because if it is outside BI, then we can find another maximum, like that would be not be maximal matching because we have one more vertex that is in matching. So we consider like A1, and if A1 has like some vertex which is like outside the BIs, then we can just
Okay.
probably shift P and A1, and that would give us like the maximal matching. Like the vertex P and A1, we can just probably shift it.
Yeah. So essentially, you are from P, you are going to the neighboring set of P, and then you are going to some vertex which has neighbors here. And if it's
Yes.
connected to a vertex which is in Y minus Y dash, then you can just swap, right?
Yes, that's the idea.
The idea is correct. The idea is very good. Like this is very similar to the augmenting path idea. Like this is our augmenting path, which is colored here. Then we can just swap this, right? But will you have such a vertex? Like that's not necessary, is it?
Yeah, that's not necessary.
But
I'm
the
trying
idea is
to
important.
disprove.
Like the idea is
Wait, we could
very
look
good.
at the augmenting part, I mean the neighbor set of the other vertex. Say we have some set uh, S which is connected to NP, which is other than P, and we could query the
Okay.
neighbors of S, and then we could query the neighbors of those neighbors, and then you'll get like a augmenting part which must eventually end somewhere.
Yeah, and why does it have to end?
I've not gotten to the part, but one second.
Yeah, you're on the right track. Yeah, I will give you guys time. You're doing really well.
Okay, we have to show that this ends up in a play of like in a point of in y minus y dash.
Wait, Nishant, how are you trying to construct your augmenting path? I didn't get that.
We look at P and then we look at NP. Then we look at the S, the AIs which are connected to NP.
So S is a subset of X. Huh?
Yes.
Okay. Then
Then we look at the neighbors of those in y dash. Like if it's there in y minus y dash already we are done. If it's not, we just look at the stuff which is there in y itself, and then we look at their neighbors in x like that.
So what you can do is you can actually tweak this a bit. Like, okay, the neighbors of P have to be occupied, right? So yeah, take any vertex, go to like the neighbor, like from P we went here to like here, and like we travel across the original matching because then we are essentially trying to construct a larger matching, right? And we are on a hunt for augmenting path. And we do the same algo, like we just go to neighbors and travel across the original matching. That's the only tweak I'm making. And yeah, you will eventually you'll eventually have to like end to an unsaturated thing.
so if the neighbor set of P has a vertex in the matching, then we're done. But
Sorry, can you repeat?
if in the neighbor set of P there
Okay.
exists at least one vertex which is in the matching which we have, the current matching, then we're done.
Mhm.
And if there doesn't
How
exist,
are we? How are we done?
no, what you said, right? Because if there exists one, then you can just go to the vertex which it's mapped to. Okay, yeah, suppose in the neighbor set of P, there exists uh, there exists a vertex B, and B is in the matching. We're assuming
Okay.
that there exists a B that is in the matching.
Yeah, all of them have to be in the matching. Else we are done already.
Right. So if it's in the matching, then it must be connected to some other guy.
Yeah.
And then that's just an augmenting path.
Yes, close, very close.
By the way, the alternating paths are like all inside the matching. So we can probably use the Hall's criteria on like P and AI, and they all have to like map to like BIs, which fails the Hall's criteria.
Yeah, so what ex like you're facing a problem here, right? You are you are like not essentially you can end up in cycles or something if you go around like this, right? And this can get very complicated. So you want to sort of make a tweak that forces apart. And it's really hiding in like plain sight. Like think of the Hall's condition. Can you like think of like how great we algorithm a bit? Like currently we're just looking at individual vertices, right? We're going from one individual vertex, then we're going to another individual vertex, then we're looking the neighbors of that individual vertex and going to another one. So that's a very local approach. But Hall's condition is not very local, right? You're not using its completes.
Wait, so then we must have all the neighbor set of P must be in the matching, because if there wasn't, we could just
All the neighboring sets of
all the
Hall's,
vertices in the neighbor set of P
yep,
need to be in the current matching,
yep.
because if it wasn't, then you can just draw another line
Yeah,
and
you
you don't
can
need
just map.
matching.
Right.
And then like I think we kind of have to use the fact that in a matching we are using the same number of vertices on both sides. So
Okay.
we're gonna have some extra in Y also.
Not necessarily. Like you can have them, like you can have extra vertices, you might not have extra vertices.
Or
Okay,
you might have none of them. Might have none.
Yeah.
okay, so what if we consider this as AIs, the set AIs which are matched to P, the neighbors of
Okay.
N of P, like so, like that set. Uh, okay, we consider that. We consider the neighbors of AI which are matched to that N, the neighbors of P, the AIs which are matched to neighbors of P. Sorry,
Okay.
so like that is, and then we consider the their neighbor, their neighbors which are outside of the neighbors of P.
Okay. So you're considering, first of all, we consider P's neighbors. Then
Yes,
we went to like we consider their neighbors, like the union of their neighbors, and went to one of the vertices, like one like the set,
the
and
set
then
of.
we yep, and then we just keep on repeating that.
So why? So when will we get a contradiction that we went in a cycle? Wait.
We can consider the vertices in Y that are like that are in the like alternating parts. So that we consider like from neighborhood to uh, neighborhood of AI is in Y to like then from that to in X and such that, and we want to prove that like there is no vertex that can be outside it, because like we can consider all AIs and P, and that should all be mapped to BIs, because if not, if some other vertex is there, so like then that would also be in the alternating path. So then we can apply the Hall's criteria and say that because the cardinality is like one more in X than Y, so the Hall's criteria fails.
I mean, not necessarily like it won't necessarily work out for complete.
You can have both
Mhm.
sets have the same number of vertices. That's also in the criteria.
Yeah. Okay, so as I said, you have to actually look at the Hall's criteria. So what you always suggesting is very close, like very good progress. Like so what you okay, let's just draw another matching to make things simpler. Um, right. So we are considering this vertex, which is isolated, and now we consider its neighbors, which are these two vertices. And let's just travel through the original matching, like say this one. Now what we do is we consider this subset of vertices in X. Consider their neighbors, which is essentially a larger set, like larger neighboring set, right? And find a vertex, which we will, obviously, because we have a matching. And yeah, we keep on doing that inductively. We keep on adding one vertex at a time. At the end, we will have like the entire thing. And why does that work?
Yeah, because that in at one point you're going to take everything in X. So that would mean you have to take everything in Y, but that would also include which is connected to X, but that would also include the vertices in Y that are not in the matching. Because if they weren't, then there's no edge between them, then it won't be in the neighboring set.
So you will have an augmenting path.
Yeah.
Yeah. So is it clear how exactly we constructed an augmenting path?
No, can you like just say that again? Like my mind just floated over it.
Yeah, that's fine. So we consider the vertex, which we have been calling P for some reason. We consider the like its neighbors. Obviously, all of them are occupied, so you can travel to the vertex in X, which is part of the matching. So you're considering this green path, and now what you consider? Now you consider this subset, right? And see, since like Hall's condition is true, you will have lots of vertices in this thing, like its neighborhood.
Yes.
So you take that subset,
Sure.
and you travel. You can essentially travel to one edge, which is not saturated because this is not occupied, right?
Yes, you can travel to one edge which is not saturated. Yes.
So you can have an alternating path. You can keep doing this. You will have an alternating path. And where it will eventually end?
So we like eventually look at all the elements of X.
Yes, we will.
And okay, we'll look at Y minus Y dash as well. And it's something in like whatever we would have reached will be connected to Y minus Y dash. Otherwise, it
Yep,
Hall's criterion fails.
exactly.
Okay, that's it. Hmm.
Yeah, you're so close to proof. Come on. Like the proof is actually right there. Like the statement is screaming you to like use subsets, like inductively use subsets. Like that's what we have been doing like so far. Like the ideas is so like the theme is this the theme is just so similar. Like you have to find augmenting paths and everything. And yeah, this is a bit more technical introduction to matchings and halls. Usually we start with problems, but yeah, we are finally gonna do problems. I guess that's that's gonna invite more traction. I don't know. Anyways, so we have a problem which I don't know where I'm so okay. Search for the hook. Okay, yes, I found it. Let's go. We actually have a very hard problem that we are gonna solve today. It's the China TSTP6. Scary. Or is it scary? We shall know. Okay. So yes. Santa Claus is at least n gifts from n for n children. And the ith child considers xi of this item to be decidable. You have this weird inequality. Prove that Santa Claus can give each child a gift from like that child likes it.
Which we'll find a matching, and then it said the neighbor set for all n children is like greater than n, and then for the rest of the subsets, it's just giving you the weird inequality.
Yeah. We are exactly half a year off Christmas. Very appropriate for me to use this problem. But yeah, we're gonna still do it. I joined late, but also, by the way, there are other proofs of Hall's theorem which are, but this is the more instructive one. This one I actually saw. I think Pranjal Bhaiya had one class in Hall's theorem at some point on OMC, like back in 2021, 2022 or something. And yeah, I saw the proof there. And I think this is very instructive. It gives you a lot of insight on what the structures look like in matrix. And obviously, there are proofs which are not that interesting. Like you can assume contradiction, and actually, you can do a very similar kind of proof and prove that you can find like explicitly construct a subset so that Hall's condition doesn't hold. You can also do an inductive proof, but induction is boring. Come on, back to the problem. Oh wow, I'm so sorry. Can't seem to remove this one. That's fine, I guess. Yeah,
Okay, I can already see AMHM stuff.
yes. Back in the days, we used to call it coffee shots. But
Oh
yes,
wait,
AMHM for sure. We take that.
oh,
We take that. Okay, well, costly shots. What do we get with costly shots? How do you costly shots? I mean, AMHM. I'm so sorry.
yeah, sure. Like nobody cares about the name. I don't at least, but
Do you know it's actually called Koshi Bunyakovsky shots?
Seriously,
Yeah,
what name?
Koshi, what?
Koshi Bunyakovsky Schwartz inequality.
Like let's stick to one name and let's use it throughout or
Yeah,
something.
I think it's really unfair that Bunyakovsky has been ripped off his credits for like I don't know how many years. So let's pay him some respect. Let's call it Bunyakovsky's inequality.
I can't pronounce that, so I'll be sticking to Kwashi something.
That's so disrespectful.
I can't pronounce it. Okay, that's a different matter.
Just say, okay, I'm just going to go with the inequality.
Yes, it's the inequality. The
Yeah.
inequality is it. Okay, what do we do with Cauchy shots? Do we just do this?
Yes.
But then that gives you
Squared, which is n squared, and
divide. Got to get that.
so x, yeah, that sum is greater than n squared.
Okay, but this gives you an inequality across all and for to do anything with Hall's theorem, you need for like any subset.
Yeah,
Right.
like instead of 1 upon Ron, you can continue.
No problem. Go on.
Instead of 1 upon x1 till xn, 1 upon xn, like we could make it 1 upon x1 till 1 upon xi or something.
Yeah, it still works. Exactly.
And
You can
like
just
prove
do.
Santa Claus can give each child a gift. It's like you want a perfect matching, so you want to show Hall's condition exists.
Yep. Also, they're so nice. You have n gifts, n children. Oh, at least n. It's not nice. Yeah, that would have been pretty boring.
Okay.
Never mind.
Okay, the only issue we have is like, what if, like, in the gift is like repeated in x1, x2 till xk, so that somehow you would still reach k squared, but it's-
Yeah, like if you you go to a contest, like if you have this problem in a contest, right? And you don't know what Hall's theorem is, you're not thinking of making crafts and matching them, you're probably thinking more, I don't know, like, okay, intuitively, I don't want gifts to be common, but I don't have no control over it. It's kind of very random, and the inequality is nothing like it's not easy to see what the inequality means, like what it really is trying to say. And even if you have the inequality, how do you use it? Like if you don't know halls,
Wait, so one of these K children like at least K gifts.
no, like xi.
No, like one of the children from X1 to XK like at least K gifts.
Oh, okay, yeah,
K distinct
yeah,
gifts.
yeah. PHP.
Okay, that was PHP, fine.
Yes, that is
I
PHP.
I thought of like okay, I thought of like maximum and stuff, but okay. Let's leave that, put that
Same
aside.
thing. PHP, also known as common sense, also known as who was that? Wait, someone's lemma. I don't remember.
The weirdest name is Chicken's McNugget. Chicken McNuggets theorem. That's the weirdest name to know.
No. Chicken McNugget is different. It's like, hey, it's like some guy.
Oh,
I don't know.
we are done, aren't we?
We are sort of done, but how?
Because like at least one of the children has at least K gifts, distinct gifts. And so we consider
Oh,
the set with that kid and then you're done with your neighbor
Yeah,
set.
easy problem.
But if we did not
But
know
come
how,
on. But come on, if you don't know how, exactly, what do you do?
China expects too much from Santa Claus to know halls.
there's no way this is China.
This is not China.
Yeah,
This is
that's
very
what
American.
yeah, like
Yeah, this is very capitalistic problem with gifts and children. No. There's desire and everything. Come on.
Yeah, okay. Desirable, yes.
I think this is even stronger than hall the required halls criterion, like.
Yeah, Santa Claus is stronger than Halls, bro.
Yeah, we got it.
This year USMO problem 6 was like an insane problem on
Don't
halls.
spoil.
Oh,
Don't spoil, brother.
Okay, I didn't do this
okay,
year's
okay.
USA. Is it hard? Like, what are you guys feeling?
Do it after 6 months when you have no idea that anyone in this meet ever said it was about halls. So a difficulty with problems which involve halls is that you don't like end up realizing that they are halls. Like
Think of other
yeah,
approaches before you have done, before your brain finally steps on
But
halls
I
and you're
think
like,
like that probably if you know like even if it is all that's not like easier stuff. That's still pretty hard.
yeah. I mean, still, I don't know.
Like
It's
what do you
not
consider like X and Y to be like that's also main part.
exactly, but it still is sort of a hint. Like it's a P3, P6. Like come on, it's a very hard problem. People hate the problem for a very specific reason. But okay, okay. Let's see how in other weird situations where you probably will end up using halls. Um, okay. How do I find this photo? Okay, I saw this problem in some handout. I think it was CJ's handout. So essentially, you have a grid. Um, Credits to CJ for this, but yeah. So you have this AMSP problem. Is it like, do I need to zoom it? I think I should. Yeah. So even 8 cross 8 transport with the property that on each column in each row you have exactly n pieces. And n is in the set. Prove that you can choose 8 pieces, then no two demands.
okay, I remember the
So
question,
how?
but not the proof for some reason.
I think this is in Rushil Bhaiya's book, like the first problem in halls.
Oh really? I don't have his book though. That is so sad. He should
I
gift me.
think
He hasn't gifted me yet. That is so rude. Tell Rishil. Anyways, um, Yeah, so how would you, okay, we know that it's about halls. This is a class on halls. But you see this problem in a contest. Are you really like, oh my God, I have a grade. I'm gonna do Hall's theorem today. Like you're not thinking that. Come on, let's be honest.
No, no, no.
Right?
Not in
So
first
okay,
20 minutes at least.
yeah, you're not doing that, right? You're probably thinking, okay, I'm probably gonna do some global argument. I will sum all these columns, I will sum all these rows and find something, like find a contradiction that you can choose. Like the expected value will end up being 8.011 or something. Like, right? Or maybe you are a very, like you are a veteran in the local game. You are
But I think like
analyzing
expected
subgroups
value
and
is
everything.
like less probable than Hall's.
Like easy, you can use
You'll
like
probably be
other
trying other
like
stuff than halls, like for the first at least half an hour.
yeah, I think EV is more natural. Like it's very natural to think stuff probabilistically when you have stuff like this. Because yeah, it's hard to control locally, right? But Halls is like very unlike. But okay, do you like okay, do you all have any idea like how you would even do halls here? Like even after I've shouted like 10 times by now that it's a halls problem. How they do halls on this? Where is the graph? Where's the bipartite graph? What are even the vertices? What are the edges?
Okay, I've seen this as a common idea in other graph theory problems, but not in halls specifically. So you can like, should I tell that idea? I don't know if it's true.
Yeah, feel free.
Maybe rows and columns.
Yeah, exactly. So it's very weird, no? Like as a first, like if you have not seen this before, because it makes sense to like consider these cells to be vertices, right? And the neighboring things to be like edges, right? That's a natural idea. Someone can come up with it. But you instead consider a whole column and whole row to be vertices, and the edge is actually the unit cube. It's like very
Yeah,
smart. Like
and your things are the now your dots are the lengths, their edges.
yeah, and now it's not that hard to like confirm like that Hall's condition is true. So you can try it at home. It's fine. But yeah, my point is that most of the times halls will be just disguised pretty well. Like, um, there's lots of other problems which I'll probably put in the preset. And if you need like a walkthrough kind of like what we covered in class, I can maybe put in some kind of handout or something. If you want that, I can do that as well. So now the heavyweight. It's China TST 2022 problem 6. So sounds hard. The problem looks hard as well. But yeah, I saw the problem actually back in 2022 when I was just like, scrolling through it. I just was like, wow, this statement is cool. But I didn't know what Hall cinema was back then. I tried it for a while, had no idea what's going on. I was just clueless.
So did you manage to
Some point,
solve it without using halls?
no, I solved it an hour ago.
Oh, okay.
I was actually not sure if I would be like able to cover this problem because I didn't know how to do it. So I was doing this like an hour back, and luckily managed to do it. So yeah, I'll take a screenshot. Oh wait, I can take a screen. Okay, I can take a screenshot. This is a very involved problem. Um, yeah. So yes. So since this is a horse class, you're obviously screaming on the top of your lungs that, oh my God, you have union of something greater than equals this. This is horse condition, even better. But okay, you have something else to prove. You don't want a matching. You want to prove that essentially you have subsets. Like you have a huge set, you have lots of subsets. You have numbers in them. Prove that you can color all the numbers in two colors, such that these subsets like have at least one black number, one white. So how do you create the graph? Don't like think too complicated or something. It's simple. Like this is the simple part.
Okay, what if we consider the A1 to AM and we consider black vertices and white vertices? Or some weird thing like that. Okay, no, that'll make it like 3 parts.
That is weird. Like let's just first come up with a bipartite interpretation. Like okay, it's just fairly simple. Like, you probably have come up with already, but don't know. But yeah, essentially consider the subsets to be the vertices, like in X.
And the elements?
Yeah, and the elements will be the vertices.
Okay, so you have false condition if you know that.
Okay, so how do you consider
Yeah.
black and white?
Wait, what?
Sorry. No,
Like
that's it.
um, how do you why is this the numbers which are in these sets? You have more numbers than like does this make sense?
Yes, but how do we encode black and white conditions?
Yeah, okay. So
That's
if
the
you
question.
had two matchings, right? Two matchings which are completely separate, then you could just consider like color one matching black and one matching to be white, and you're done.
So we need Hall's applied twice or something like that.
Yeah,
Differently, twice applied differently.
but can you actually apply Hall's twice with just this tweak? Like one, like you're just adding one. Like, does that make that much difference?
I think like somehow you a vague idea, like you first use halls to show that there's a white matching, remove all the edges, all those other edges, then what you're left with use halls again on.
But what if the white is like really big or something?
Yeah,
That's also true, yeah. It was a vague idea.
exactly. So Hall's twice is like very ambitious. Like very, very ambitious.
I think that plus one might back you up for that second usage.
Yeah, it might. I'm not spoiling. Anyways, um, let's just consider we are considering horizontal bipartite graph because when I was doing the problem an hour back, I did that. Don't question me why I'm considering horizontal bipartite. If it's against your ethics, I'm very sorry. Right? And okay, we have lots of this. One construction for such a thing is essentially everything has two things. I don't know. Fine, I guess. That's pretty nice, okay? Yep. Okay. So let's draw matching. Let's just consider the basic perfect matching we have.
Wait, so the top row is the sets, right? The top vertices.
Yeah. Wait, no.
What?
Sets are on in the bottom.
Okay.
Wait, actually. Oh, you're taking equal. Oh, the cardinal number is the same. Wow. There are m numbers. Okay, no, it's not. Yeah. Okay, let's just consider matter. This, this. Oh, wait. We don't even have matching. What? We need more vertices. Uh,
Yeah, because like A1, A2, A3. Okay, no, wait, what? Why does it look like it works? The criteria.
so can you find two matchings here? Oh my God. Okay. That was not intended.
Wait, it's not a perfect matching.
Is this no? It is.
Oh,
Matching.
all right. Yes. Yeah.
Okay, I'll just clarify. This is the subsets.
Okay, so the union of like
This is
X
this.
subsets has at least X plus one elements. As
Yeah,
far
that's just Hall's condition plus one, right?
Yeah.
Like, just to make it clear, I will, um, no, I will do nothing. Sorry. Okay, I will do something. Like, yeah. Yeah, essentially have this word, like any subset S. What do you do now? Try to consider another matching, as we said.
so we perhaps take our matching and delete the matching edges. We have
Let's
at
not
least one
delete
match.
it. Let's keep it here. Like,
Or
it's
why
not
don't
been a
we
lot
take
of
like
time.
what we did before I forgot the name, the difference of them. Like, remove all of the
Yeah, symmetric difference.
symmetric difference.
But you essentially remove all edges then. Oh wait, no. Wait, symmetric difference. Okay, I get it. Okay, makes sense. Yeah. So let's just draw the matching first. Um, that works. It does. So you have no overlaps. That is some. Then the symmetric difference is just this. So you get no information. You're just back at it. This is not intended. I'm so sorry. What can you do? Maybe consider the ones like, okay, where do we face a problem? When you have like these things coinciding, right? Just mark these. These are creating problems. Else we can just color black and alternative. Um, these are causing us real problems. These are the vertices which are we sort of have to think before we assign a color to. One thing that this condition allows us to do
Wait,
is
if you don't
that
mind, can we do the case when it is three, like we just take three subsets, like A1, like M equal
sure,
to 3, because M equal to 3 or M equal to 2, like
m equals 3. Fine. Okay. Okay, now symmetric difference actually makes a difference. Two perfect matches. Okay, what can we actually do?
but
Let's try coloring.
sorry.
Let's just try coloring. This is black. This is white. Right?
Wait, I'm getting a feeling this. Wait, look at A1 and A2, and it has only two vertices in the name. Okay, three vertices. God.
This coloring works, right?
Yeah, that works. Yes. Okay,
So
so
whatever.
the black vertices are the ones which have which have only one color on them.
No, 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 no. I'm not specifying it like that. I'm just considering one coloring that works. Because suppose we color this black, then this has to be white.
Yeah.
Then this vertex, for example, this is white, so this has to be black. And this is obviously white. This is this.
No, like if you see the ones with white have two colors like coming into them. Like, both of the matchings
Okay,
have that same white vertex, and that's for both whites. So if we can color it that way, does that help?
color it in what way?
That the whites, I don't think it's true, but like if that the whites are the ones which have kind of both red, both matchings have the same vertex. Those are going to be the white vertex.
Okay, okay. Color doesn't really matter, but yeah, I get what you were saying. So essentially, if they have same things coming out, they have to be like they are like not monochromatic. Okay, let's try to consider like construct a contradiction, like in the bigger graphs. Like, so this is black, this is white, then this is white, black, white. This is black. Yeah, like oh, then you do run into problems. But uh, I don't think. Okay, it might be this actually. Interesting thing.
Wait, so what exactly do we want in reference
Oh,
to halls?
we so our initial idea was that we could if we could find two matchings, then we could just do it. But in what happens is that stuff coincides, right? Because the condition is not that crazy.
Yes.
So what do you do about that? So okay, one thing I was saying earlier was I couldn't finish saying it, but like yeah. So what this condition actually allows you to do is you can actually choose to not have a vertex in the maximum, right? Like in Y, for example, you choose this vertex, and yeah, if you don't want it to be in the matching,
Yeah, I
because
can leave it out. Yes.
yeah, just leave it out because Hall's condition is still satisfied, right? So, and then you consider matching, for example, and then you could probably do it to have different colored vertices. right? You color the left out with black and the other one is white, like the one that's matched. Maybe something like that. And by the way, Ronit, your idea, I'm pretty sure it's not true. And yeah, but okay. I will not completely rule out your idea. But okay, how would that help?
So how many blacks do you get if you keep on excluding it out of the matching? And then somehow you can show that all of those blacks collectively are in another matching of their own.
Right. I'm actually not aware of a proof that uses it, but yeah, that might be pretty cool. I'll definitely think about it.
Like kind of like the blacks that you're excluding are going to be a bit random then.
What actually happens is that's not one of them. Yeah, but then I don't think this is true. I will tell you why. Because here, for example, the
Oh, no, I was talking about your coloring.
okay,
Yeah, in your coloring, if we suppose always exclude one out, so
okay,
then we colored those black and white. We obviously have a matching with white.
yes,
So now we have to kind of show that we always get a matching with all the leftovers black that are black.
yep. No, what I was saying is like in the claim you had, I think it doesn't work because essentially this is very like this graph is very interconnected. Like, do you see like where I'm coming from? Like you could have that you have like entirely two different groups of things where they just don't have so much in common. Like you could just have independences and then you could color differently and they would have
Can we like make copies of elements?
how exactly.
Like if since they're coincident, like if they are coincident, we just make two of that type and connect one to each.
Okay, okay.
Because like I otherwise like the perfect matching idea does not fit in my brain for some reason. Like how will we use perfect matching in that in any other way?
Yeah, yes, exactly. Like although it's very similar to Hall's condition, we don't seem to get a lot of information out of it.
I feel like if we can get that the number of black edges we keep on excluding is
Okay.
greater than the number of vertices in S, then we are done. So we can kind of need to count the number of black
Yeah, you
edges,
could just solve
black
it then.
vertices. Yeah.
Sure. Okay, let's just return to our original graph. It's very hard to draw these. Okay. It was just so painful. Oh my God. I'll just remove these colors. Ah, okay. So what we were doing is we will consider one vertex, which was we decided would not be like would be excluded. Okay, let's just say the blue matching is the one which we did after excluding that thing. And
So they're
then
the
we could,
whites. The
okay, sure.
okay. Yeah. Just
Like this vertex, right? So this is white. Also, oh, if you notice one thing, um, stuff like this might actually help because these vertices have black edges, as in those which are not in the matching at all, right? So when you have stuff like that, you have augmenting paths. So you get some amount of freedom to tweak the coloring. Like you can just change the matching a bit maybe just to fit the coloring, right? That's some that's just a point I'm saying out loud.
Yeah, I was trying like with your idea of like excluding a vertex. So like we consider some S first, like to start off.
Yeah,
Perhaps
so let that vertex be this, like S or like what do you want to label it?
isn't
G.
S the sets themselves?
Okay, are we having abuse of notation? Oh my God. Anyways, tell me a labeling for this vertex.
Wait, S is in X or Y? Like first, let's.
Wait, S is not, we haven't defined anything to be an S.
Yeah, exactly. So is S in your description of S, Nishant, is it in X or in Y?
I was thinking of like S and X, unless I read it wrong.
Right. Yeah, basically the S we're using in that
No,
condition over there.
you can't be excluding a vertex in X though. You're mapping from X to Y. You can only exclude vertices in Y.
Saying ki you consider S and you consider neighbors of S which you can remove, of which you can remove one.
Okay, let's just first consider that vertex. Like let it be V. And you were considering the neighbors. Right,
Fine.
sure. What do you do next?
What if we just remove one of the edges? Like we just ignore it because since Hall's criterion is still satisfied. It will,
Which edge?
it will Hall's criterion still be satisfied?
Like we already have used 1 degree of freedom excluding that. So would you want to do it?
I don't get what are we excluding. Wait,
Okay, so okay, look, this condition gives you 1 extra degree of freedom, right? To do something.
correct.
Does that make sense? So this is intuition. This is not something very common. So this allows you to like what we did was exclude one vertex to be in the additional matching and another matching which has it in. So we have sort of used this condition, right?
How have we used it? I still don't understand.
Like if you didn't have this condition, for example, if you had n of s dash greater than mod s, you would have a matching, you are happy, right? That's
Yeah.
it. You can't really do anything after that. But what
Yes.
you are doing here is you are considering you can construct two matchings.
Yes, we want to construct two matchings.
Yes, so you have like sort of used this extra degree of freedom you had. So what you said, it might like this condition just might not be strong enough for us to be able to do
Okay, what I was thinking was like you take every vertex in X, look at its neighbor set. It must be at least two, right?
that. Okay.
So now you take one out of that, like just you exclude that black out because you can, and
Yeah.
then you do the same thing for every one of the vertices in X. So now you've kind of partitioned it into blacks and whites already. So you
Not
know
really.
that
You would have paths. You would have paths like this.
Except, wait, what if we take coinciding edges and exclude those? Like coinciding edges must be better, right?
Yes, you can exclude coinciding paths sort of because they are like sort of like self-looping. To think
Like
about it.
because like you just need to exclude one and then like they handle both to
what do you
exclude.
mean? What do you mean exclude the coinciding lines? What are the
Say we
coinciding?
excluded V, then we exclude included the extra degree of freedom. Like we've used the extra degree of freedom in both A1 and A3 and A1
No.
union A3.
No, like what do you mean by coincident edges?
Coincident means like
Like
an
the
element which is in two sets.
yeah,
Okay,
that
so
makes
like the
sense.
white over there, which was just drawn.
I have no idea. It's written V as far as I can see.
Where is it?
Okay, like this
Oh
one.
yeah, that yes, yes. Okay, fine. So
Like
you
that.
remove
Okay.
one of the edges.
No, I'm talking about like we remove the point which has these coincident edges. Like the common element, we remove it since like we can remove less common elements and we can use up more degrees of freedom.
Okay, yeah. Then you first start by removing all of these other these things. Now you have partitioned into blacks and whites, correct?
Have you?
Huh?
Have you? I don't think so.
No, like for every vertice, you pick one black out and you have one white in, right?
Okay.
Okay, so you're saying that if you remove these excluding things, then you might not have a
Yeah,
white left.
the problem is that you just can't do that. Like you will have some
Then should we
vertex.
remove the excluding ones?
See, I was thinking of
Um,
removing the coinciding ones because like we'll still have the mod S plus we'll still have the mod S note, but we'll have to remove less coinciding things to get the required Hall's criteria. Right, unless my thinking is warped.
yeah, but I don't think you will get like the Hall's criteria again. I think that's a bit too like expecting a bit too much.
Like, how do you know the number of coinciding is now going to be greater?
Yeah,
Greater.
you might.
Like, how do you know that the number of
Okay,
coinciding vertices is not is so huge a number that it actually removes your Hall's condition? How do you know if that's true?
No, I'm just
yeah.
choosing some coinciding vertices, not all. I'm choosing some so that the Hall's criteria is satisfied, but it's just satisfied.
What
Okay,
if
so you want
that?
equality.
Wait, but what if I remove some coinciding edge and like the coinciding edges which are left over are itself less than, yeah.
But you could have a weird special case where just even removing like one vertex just messes up, like one edge messes. Right.
Okay, can we prove that exists another augmenting part outside our first, like outside the first matching?
Why would there exist?
Good question.
We already have two perfect matches. It's fine. Take your time. It's a hard problem.
But like, why do you want an augmenting path?
Because then you have
Yeah,
no
you won't
matching.
have one. You won't have. You already have two perfect matches. You constructed two perfect matches with the condition. But the problem you're facing is that some vertices are common.
Nikhil
So,
is asking, can you share the problem?
oh, the problem. Yeah, this is the problem. Yeah, okay. Let's just draw in a bit fast. Because why not? Make some simple. Or maybe this is good enough. It's getting so complicated. Oh my god. Imagine if I actually solved the problem wrong. Wouldn't that be crazy?
It will be more interesting, I would feel like, because you've got one extra mind to work on it.
Yeah.
Yeah, come on. Like, I'm probably as clueless as you on this problem. I just solved it. Like I don't know much about it. I know it's a good problem.
Oh yeah,
Understood.
he
Okay.
didn't get to take a screenshot of it that time, it seems, of the problem.
Oh, sure. It's China TST 2022 P6. You can find it on the playoffs.
Okay, so the problem is that when you're excluding your black, then you don't know that you might have some coinciding things, coinciding edges, such that you will have less number of whites. That's the issue right now.
Hmm.
I was more annoyed by the issue that what do we do after we get to matchings, as Debayu said.
No, because what I was thinking was that if you don't have the coinciding vertices, if suppose they weren't there, then you would have a matching with white and you would have a matching with this black, right? Because you're taking every vertice in X. You're having you're gonna have at least two of them in their neighbor set. You exclude one black, you exclude one of them out. You do the same thing for every other vertex. So now you have a set black which you know you have a matching with, and you have a set white which you also know have a matching with. So that finishes the problem. But now the point you can have these joining
Yes.
vertices.
Yeah. Okay. So I'm constructing a much simpler thing because this was getting messy. Let's just consider a very simple graph because I'm pretty sure that by now you know how these work. I don't need to draw extremely complicated graphs to confuse you. This problem is enough. So yeah, so we are drawing two matchings. This is obviously a matching that works, and we have excluded this vertex. You know what? Let's just exclude this one because yeah, then it's just easier to work with. I don't know. Just OCD. Bear with me. Okay. Okay, let's just not this to this. Now, okay, we excluded this. Now we want the matching with this one. This, 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 this. and, uh, This? No. Oh my God, no. This is not true. Oh wait, is this even true? Like this one is.
Wait, what?
Never mind, never mind. Our old graph is much better. I'm so sorry. Okay.
Okay.
Just like copy
Yeah,
paste it or something like and clear out the unnecessary.
I don't know how to do it. I'm so sorry. I tried. I'm such a boomer. It's the first time I'm trying in this software. Like, Excalibur. Apparently it's good. Yeah, it's smooth actually. Anyways, so let's actually consider these two matchings like independently. Like,
Wait, so if we have
two.
such constant edges, we have some edges which are left out, right?
What do you mean by left out?
Like they haven't been colored in both matchings. Like they aren't present in both either of the two matching.
Is it necessary? I don't think so. Like, suppose these are the edge sets of the two matchings. These are like one, two. Like, like E1 is the one branching off from like, one, F1. Like, yeah. So, what? Okay, let's consider what happens to like this. Like, let's consider these. Just pair them up. Let's just see what the structure is. Because these, like, the V's are what we are worried about, right? Like these V's. So let's sort of try constructing paths or like cycles because then you can sort of relate these V's, which are kind of like very abstract right now, but you can maybe connect them together because covering an even cycle, for example, is very simple, right? You can just two color it like easily.
Wait, I didn't get your idea. What was it?
So the V's are what we are worried about, right? Like these are very tight
Yes,
numbers.
yes.
So let's just consider like EI, FI, these edges, like these edges, because they have the V's, right?
Okay, EIFI was what again?
So if we have vertex I, then EI is the same green one and FI is the blue one.
Okay, fine.
So you consider like these edges, you can direct them if you want. That's
Okay, we
on
want
you.
the cycle over all the bottom ones. So like if you want an even cycle which goes over all, so we can color some of them blue and some of them green, if I understood the idea. Like
No, like I'm talking about coloring black and white.
yeah, like we
Like
color black and white. I'm saying we construct an even cycle and then we like going through all the sets or which or whatever vertices on the bottom row. And
no,
then
but
like
constructing an even cycle is very ambitious. Like obviously then you would have a black white color, right? Like
yeah.
that is very, very ambitious. Like will that work? But still like
Do we
um
need that first is the question.
Okay, wait.
yeah,
I'm still
you
trying to
probably
understand
don't.
why do we want even cycles like
Because even cycles are kind of nice. You can two color them very easily. And that is the problem. You want to two color stuff. But yeah, this is very problematic. This is not that simple because you also have these vertices in the cycle, right? So we are not explicitly considering even cycles. We are just trying to simplify the structure with these directed edges because they sort of relate the greens and blues. Does that make sense?
yeah, yeah.
Wait, I don't get it.
No. So sorry, I actually do wrong. So we are considering what
So you
what am I
always have an
doing?
even cycle actually, if I'm not wrong. Right. Because if you start at a vertex which is if you start with a V
Okay.
and then you go along the green side and then that's going to be incident on some other vertex in X
Mm,
and then that will be connected to some blue and now
yeah.
if that thing is if the blue that it's connected on if it's fair on the blue if it's connected on the okay yeah maybe not.
Yeah, okay. So I get what you're trying to say, but that is not really what I'm trying to say. So intuitively, what I'm trying to do right now is I want to understand the structures of these V's, right? That is what I want to do.
Right. So like you're considering them as like connections because you want one of them to be black, one of them to be white.
Yes.
Okay.
So like
So we will sort of have a network.
okay, like some of what like jumping V's, like oh I don't know what you call these
Yes.
jumps.
Yeah.
Like so you could just like jump like if they're in the common vertex, we just connect those two by a jump or something. Like in a common set. So like can you like name the vertices at least? Like it's getting hard to.
Yeah, I will. Let's run it. Come on. Okay. I need an edge. I wanted to make this graph interesting. Uh, I'll erase this one edge.
Can you
I'm
copy a
gonna.
graph? Can you copy the graph which you already have and paste it, or does that work?
I wish I could do that. Okay, I will. I will finally try this properly. I will use the snipping tool, the mighty
Hey,
snipping tool.
okay, you just snip it and then you'll paste. screenshot.
Yes. Oh my God, this works. What a genius I am.
Like you can just expand, I'm pretty sure. Yeah, yeah.
Yeah, there you go. We have our deer graph.
So let's draw all the hops or whatever jumps that we have.
Yes. So this is 1, 2, 3, 4, 5, 6. Yeah. So wait, this is actually bad. Wait, bro, do you realize this is not these are not two perfect matches? This is actually kind of
Yes,
bad.
yes, they're not two perfect
Yeah,
matches.
we need another vertex. Oh my God.
Sorry.
Now it's a perfect matching.
Yeah.
No,
Now,
no,
how do
no, no,
we?
no. No, no, no. Add 6 to some other thing, right? Just add 6.
Yeah,
The
I'll just
6,
add this.
yeah,
This
add
one.
another green.
Yeah, this
Yeah.
works.
Okay,
Now, what
Nishan,
are
the
we
problem
doing?
must be the green wasn't a perfect matching
Yeah, and nobody noticed. People are not paying attention. Oh my.
before.
We're dying on understanding what the hell are we trying to do? What else? What are you expecting?
Yeah, let's make these disappear. Since this is a snip, if I like try to like erase it, like everything will be gone. So I have to
That's
actually
the
do this.
biggest eraser I've ever seen.
Yeah. This is not even eraser, bro. This is like the brush with a white ink.
Wait, so yeah, I like the jumping thing. So like, could we like do the jump at least, like, and see how?
Yeah. Let's EIs are blue, FIs are red, like green. I'm not colorblind, trust me. And we go from EI to FI.
These are edges, right?
Yes.
Okay. Okay.
And this is a hop. Um,
And a hop only occurs if they both are connected to one of our incident vertices.
this is also a hop.
Like, no, we go in one way. Like, come on, like,
This is a hop.
Yeah, so a hop can
Um,
only happen if those two vertices are connected
yeah,
in the
these.
matchings.
like, why don't
Yes.
we want consecutive hops, so as to say, why do we want this disconnected hops?
Because that's the graph we drew, brother.
What? But
Yeah,
no,
It,
you
okay.
have, you sort of have a consecutive hop. Thing is, if you have a hop like this, right, like this orange hop, then you can just color alternatively and you're done, right? Because it's just ends, right? You can color these three, right?
I didn't get
Like
that. I did not get that.
consider
yeah,
4, 6,
okay.
and their neighbors. You can color them alternatively and you're done. White, black one.
Okay. So that. Oh, so right. Then what? What
But we had
happens?
a green and a white, green and a blue there, the black
So
one.
if you have like these paths,
Yeah, parts
you
of
can color.
jumps.
Yeah, these, yes, the paths of jumps. These are nice because you can color them alternatively,
Right. So we want to
and
show
you are
that we can
done.
kind of do it from the beginning to the end. Or not exactly from the beginning to the end. It's not necessary.
Yeah, I actually missed one hop. Yes. Okay. So we can sort of, if we are somehow able to like separate this as like disjoint subsets of these, we are done. That is too much like to expect. So first of all, let's just remove everything that is a path of hops, right? We can remove them obviously from the graph because it doesn't affect the rest of it. Like the vertices 4 and 6 don't really affect the rest of the problem.
Okay, because we could color it white, black, white, and then both are
Yeah.
happy.
Okay, yeah, so
Exactly.
it's kind of like the cycles we had before, just remove them.
Yes. So just black, black, white. This is done. Now, what do we do if we have some cycle like this?
Yeah, so what would be technically the questions now? What would be the structure after removing all of this?
Yes. You'll have loops. You'll have weird things going over this. And these are not nice.
You'll have loops, loops as in?
As in this one. Like,
Disconnected jumps, right?
yeah.
Okay.
Disconnected jumps is still fine.
Disconnected jumps are still fine. Like,
Disconnected jumps are essentially these parts. Lots of them, right?
And you don't even know if do we know that if a vertex that there exists a vertex where no jump is coming in or out of them?
And then just ignore.
Okay. But does that? But then, what color do we give to them?
Will it matter? Wait. Come again.
So vertices which are not part of these jumps.
They will be like, they have to be.
Yeah, okay. Why?
The others are, the other ones will just not be part of the matching. It doesn't matter. You
Okay.
color them anyway.
All right. Right. Yes. Fine. So we have kind of
we can kind of ignore 3 and 5 as well.
You can ignore 3 and 5. Why is that?
Because
Yeah, you can. Yeah, you can. Exactly. 3, 5, 4, 6 are gone. Right?
yes, and 1, 2 is looking. Okay, what do you
And
say?
essentially, yeah, 1, 2 is like easy to color. So essentially, you can, if you separate all of these, you just end up with loops. Like loops might be something like this as well. Like it could be like, I don't know, it could be something like this.
Well, like, can you draw the black, I mean,
Yeah,
blue and green
I
just for
will,
this
I
one?
will, I will, I will.
Thank you.
Is this possible? Hopefully. Um,
No. Oh, yeah, right. This works. Right. What am I saying?
so what do
Question
you
comes
do?
like, what do we do with loops? How do we color the loops?
Yes.
so we want to show that in the bunch of these disconnected loops, we can somehow do some coloring.
Yeah. So first of all, if it's an even cycle, then the coloring is obvious. Just do alternate coloring, right? Like this one, for example, like 1 and 2, right?
1 and 2.
An alternate coloring will work for an even cycle.
Wait,
Like
wait, what if all cycles just don't exist? Like if we have a
Is
hot
that
cycle,
necessary?
like we have like some path which like removes those two vertexes.
no, you can't have that much degree.
Okay.
I guess not necessary, right?
Yeah, you won't have that much degree. It only happens when you have a vertex that is not in the matching. But for now, we're just considering the ones in the matching. Let's just clear up that.
So wait, just to be clear, we are assuming that we already have two matchings, green and
Yes.
blue, and then we are trying to prove that we can color the green and blue matching in such a way that it satisfies.
As in, like, yeah, we are trying to prove that. So what I'm trying to tell you is, like, if we don't have any interruptions from these edges that, like, which are not part of the matching, then if you have paths were done, right?
Right.
Yeah.
If you have even cycles, like the one here, 1 and 2, then you can just color alternatively and you're done. Like black, white, black, white.
Wait, what even cycles? Which even cycles?
This one, for example. Like this is a self loop.
Okay, that to that. Then
Can we even color
That's
this word cycle?
no, wait,
like
what's the
color the
cycle?
vertices, not the edges. Like you get the
Yeah, I'm
point.
saying, yeah, coloring the vertices, like the top vertices. Can we even color this three odd cycle, like three cycle? What is this? 6 or 3? 3?
Which one?
This one, like the one you've drawn below, like
This one, yeah.
3 1. Yeah, the 3.
Like black, white, black works.
Black, white, black. I mean, don't
No, it
they
doesn't.
have?
Oh wait, oh, it doesn't.
Yeah.
When you mean by a cycle, you mean something like one going to okay, so a blue edge which goes into one, then go through the green, then through the blue, and then back to the green. That's your cycle. Or what's your definition of a cycle?
My definition of cycle is through these like paths, like the kind of paths we just like
But
jump.
your paths are disconnected now because all of the paths you already have are removed. So all of these jumps are disconnected, right?
You can have loops like this.
But won't something like that, like two humps like that, won't that be considered a two-way path? Won't that be considered as a path?
Alternate coloring doesn't work
You
here.
can go
Oh,
both ways.
so we want to show that everything else is made up of cycles, huh?
So what we have understood here is that this kind of configuration is kind of bad.
Like it
Oh, it's
doesn't. I don't
bad.
think we have a coloring
It
also for
doesn't
this
have
one.
any coloring. Exactly.
So we have to show
Okay.
that this configuration. I don't think there's a coloring for any odd.
Yeah, it doesn't. So what are we missing out on? So are you telling me like these kind of things can't exist?
I mean, as per the question, that's what it's saying, I guess.
But you forgot about the edges which are not in the matchings.
Oh wait, which were removed in our
Yes.
okay alternating path guy. Oh, what? Why are we coming back to alternating path or augmenting path?
Yes, it's a loop.
Oh, oh,
So
oh, God, yes.
so as the problem states, it just says that like any edge like the has to be alternate color, like black and white, right?
Yeah.
And we got too ambitious with the matching idea.
Yeah.
Okay, so what happens if you put those remaining edges back?
Yeah, good question. That is what you have to think about.
Let's do this.
So I just realized we're really running late on time.
Wait, what time is it?
8:22. It's been at least 2 hours.
Wait, was it supposed to be like 8:30?
It was supposed to be 7:30.
Oh, seriously?
Yeah, it's supposed to be 1.5 hours. But oh well, this is a hard problem.
Okay. I don't actually see what we're trying to prove right now. What do we want to prove right now?
We want to find a coloring. Thing
Given
is,
two such matchings.
yeah. When you have
Right,
parts
but
like
then
this, it's all fun and games.
But
But you sort of have to use, like when you don't have these hops, what do you do?
if you have odd cycles, we have to consider the remaining part if we have odd cycles.
Yes.
Like, how do we know our alternate, like our path is like optimum? Like coloring the path black, white, black, white. How do we know that it's optimum?
Yeah, that is
Like,
hard
there's probably some way
to,
to accommodate the rest by coloring it some other way.
like it doesn't matter though if it's like completely independent. Otherwise, it's not. But then alternate coloring is the only way. You just have two choices, right? Either you start white, black, or you start black, right?
Hmm.
Like the paths have to be colorless.
okay, I don't see where our other edges even come in. Like, how do they even help?
Let's just draw a few of them. There you go.
So, do we have an odd cycle in this graph?
It's a bipartite graph. Like
Like odd
sounds
cycle
like
as in like the way you showed us, like the
yeah.
odd loop or whatever.
This
Loop?
graph doesn't.
Okay, that. Uh, no, wait. What do you mean odd cycle? Cycles
Odd
of
loop.
blues and greens, huh? Only blues and greens,
Yeah.
or including the.
Yeah. Like, see, 1, 2 is a even loop.
Huh.
So, like that way, we want to find some, like, say 1, 2, 3 was an
But
odd loop. It doesn't even exist now.
1, 2 is.
1, 2 is an even loop because
Yeah, because.
one has like is connected to like has a blue coming out of it, and whatever it's connected to has a green, and then you have a blue and then a green.
wait, I'll be right back.
Right.
You know, what if odd cycles don't exist at this point? Like, wait, what if I swap the colors in an odd cycle? You know, that'll make stuff weird.
How does that help exactly?
You know, I thought we could swap the colors and then we could show that we could swap the blue and the greens, and then we could like pair up the rest in such a way that it all just works out. But
I forgot to color. Okay, I'm just considering another like graph to make things a bit more. Clearly, we are all of us are in a lot of things. Um, this was okay. We want some edges without not really must.
Your voice is a very faint.
Is it okay now?
Yeah.
Yeah. Good. Yeah, so this graph, I don't know, just randoms. Okay, so let's just draw the hubs. Oh wait. Okay. Ah, okay, no, I colored blue already. So let's go from red to blue. If you want. So this graph, for example, has one of these things we fear,
Wait, no, we
right?
could go like from that red to the last blue as well. Like, I mean, the
As
fourth
in,
top vertex. Like, we could go to the next blue, right? Like, we're going red to blue.
uh, we, we, oh wait, yeah, yeah. So this is something we fear, right? You can't alternately color this.
Wait, do we have an alternating path which like gets rid of this? Augmenting path which gets rid of this.
You probably don't. Why would you not? Like, yeah, stop thinking about augmenting math. You're perfect mathematics. Come on. We have come far. We've come far with it. So, okay, let's focus on this one because this indulges with the path thing, right?
Your voice is again a bit faint.
Hello. Okay.
Yeah.
Yeah, so we're focusing on this vertex because we sort of have a weird edge that's going to this and not part of the matching.
Oh yeah, what if we color that blue?
Um,
And then we like look
why?
at the blue one,
Why?
which makes it fail, and then we look at that, we color it. We just leave it alone, and then we move on to the next one, which is blue.
Even if you color it blue, it's still an odd cycle.
Or like we color it blue, and then we change all the previous blues in such a way that I don't know, I can't texture it
Yeah,
completely.
yeah, you can't do that for a specific graph. It's hard to do it like formally for every graph.
Okay, what are the paths like we can throw away for now? None, right?
Nothing, almost nothing.
Nothing, yeah, because you don't have any odd paths.
So we just somehow want to remove this vertex, like just get rid of this, so then the coloring is just much easier. Or like use it for an advantage, right? Because this odd cycle here doesn't let us alternately color this. So depending on this coloring, you have to somehow color this V. So it actually turns out the most annoying V's are the ones which are like single colored because these ones are much more manageable as we with the path thing we did. So like this vertex, it matches with these. What can you compute?
Could you repeat your thing once?
Yeah, so we are focusing on this vertex
Okay.
because because obviously odd cycle bad, and
Right.
it matches like these two vertices,
Right, so I
right?
don't get it. Like, let's look at the black one, the black edge coming out of S or 5, whatever we've written. So, like, we look at
Um,
that, we colored blue, and then the blue which is connected to the other vertex, which is connected to through the black edge, we
Yeah.
colored black, and then we
yeah,
colored the last one blue.
yeah, that works. But how would you generalize it?
Okay, so now we wish to generalize it. Okay.
You have a black augmenting path. Now switch the colors. Right?
It's not an augmenting power.
Okay, you have a black. Yes, yeah, it is. Right. Isn't it?
Why would you have an augmenting power at the first place when you have perfect
Yeah, but here it's an augmenting path, but why would you in general?
Okay, so now we have to use the condition in the problem or something. Wait, but
Is
just
there
oh, sorry, Raj.
okay, yeah, and is there any part of walls that we are not exhausted? I think we have done with whatever we have done with each.
Yeah, we are done with the house, and we are very close. You are missing something really easy.
Like I feel like there's gonna be some simple thing that's gonna pop up. I mean, like, why didn't you think of this?
Yeah, it's a very simple assignment of colors. Like
Yeah, Nishant, like
Yeah, so if we color blue and black, like if we switch the colors, like we will have a coloring then?
so, you are thinking about switching or matching, right?
Yes, at some point in
So,
time.
but I'm claiming that this matching is good enough.
This matching
Like
will
this
work.
matching is good enough, but like okay, this matching is like good enough, but like even not necessarily coloring like red to be black and blue to be white or something like that. Like you are utilizing this much.
Okay.
okay, what do we exactly want to show with that vertex?
Okay, look. So focus on this, right?
Yeah,
If this is connected to a path like this, it has two possible coloring, right? Like if it's black, then it's white, black, white, black. If it's white, then it's black, white, black, white. Like there's two possibilities.
right.
So just color this anything, make it white,
Okay, fine.
and make this white as well. Make this
Okay.
black. This just works.
Okay, so the one directly above our vertex is white. The one on its right is also white, and the one on its left is black.
Yeah, so all you have to do is you have to hunt for these vertices, right? And like if it's connected to a path, then what you do is you just because the path has more independence in coloring than a cycle. So you can have like these vertices will have one black thing in this cyclish thing and the white thing in the path thing. Like without the loss of identity. Can be vice versa as well, like white and
Wait,
black,
so
right?
what coloring did we do?
So essentially we are pitching the idea of coloring blue and red matching to be black and white. We essentially assign the black edge vertex to be any color we want. And then we get when then this gets fixed. This or this gets fixed and they have to be the same color. Like and then this gets fixed. And then you can just alternate the color. You will have two consecutive, which is fine because of this vertex, and you just alternate the color.
So, do you want to show that at least one such vertex exists?
If it doesn't exist, false condition will not satisfy. Like the condition we have won't satisfy.
So what do we want to show about we want to show that
Oh, we are done. Think about it. Why can you find such a edge? If you have a
I mean
circle, let's say.
because your black edges would be connected to something. So shouldn't you be done?
Sorry.
Your black edge is going to connect at least two of them. So you want to show that at least one such vertex exists. So what do you want to show about the vertex?
I don't want to show anything about the vertex.
Then
The coloring simply works. If you don't have such a vertex, then
So wait, can you like repeat the coloring just once more?
okay, so like okay, I just color it. White, black, white, black, white. Then this is black, this is also black, white.
Okay. Okay, so we have to look at the black edges more carefully. Okay.
And do you know why this exists?
Okay, there must be a black edge connected to a odd cycle. Yeah, are we saying that?
Yeah. And this exists because you already ruled out all the hop paths. Come on. Like all the simple paths you can already simply color anyway. So all of them get ruled out anyway.
also you're only left with odd cycles, and since there's at least one edge, the black edge, so you're done.
Yeah. Cell
Okay.
like even cycles and these paths we have moved. So all we have
Oh.
left us is odd cycles and these.
Finally. Okay, let's go. We'll solve the problem.
Wait, hold on. What? Wait. How does that finish? Wait.
See, yeah, we removed all the even ones, right? So now we're all left with odd. So since we must have at least one edge, we're done. We want to
Wait.
show
So
that
why
it
will?
exists
How do you know your black edge was not connected to a path?
because we already removed that.
Yeah, because you removed everything else already.
But you might have like removed the black edge along with your path.
No, you don't do that. You can't do that.
Wait,
You
what
can
is a
only
black edge
remove
defined as? Just
black
the
edge is
edge
like
which is in
not
neither
matching.
matching.
Yeah.
So the black edge isn't in either matching, and you're already removing the ones which are the paths. So you're only going to be left with odd cycles. And since there's going to be at least one edge, you're done.
Oh, wait, so if there is a black edge, we like keep the black edge and delete the rest in the path, like the circle, like the
No,
black
we are
edge, which
not deleting black edges. It's just a special case where we have only one black edge. That's why it looks like we have two black edges. We are just using it to our advantage.
so we just need one black edge. I'm like we need a
Yeah,
one black edge for each odd cycle.
kind of. If you didn't have black edges, then yeah, Hall's condition would just die because you don't have enough.
So why would Hall's condition not satisfy?
Number of edges will be just much less. You have the plus one condition.
Okay, plus one. Okay, right. Okay. Oh, right. A loop has exactly the same number on top and
Yes.
bottom. Wait, no way this was the idea. What?
Yeah. Okay. Okay. I probably didn't explain it like very nicely. Like it could have been much better. But yeah, I think it was a very cool problem. Because this is not your standard Hall's problem where realizing that you need to use Halls is hard. It's actually quite the opposite. You already know that okay, this is literally Hall's condition but stronger. Like if you are an experienced contestant, then you probably know.
Wait, so
Like
how
the
do you
chances
prove
are
that we have two distinct matchings
that
by
was
Hall?
by the plus one. Yeah,
Sorry?
that's what you did was you picked one vertex. You can exclude that vertex of the first matching, and then you can find a matching with that vertex.
Okay. Ah, I see.
Okay, that was a ride. Yeah, so I will send the problem set and probably the walkthroughs bit, and I'll really try to like. You guys really never look at the solution? Oh, I do. I definitely do look at the solution.
I do it like the
Yeah,
last moment, like when nothing really goes your way.
By if you
yeah,
have a couple of hours of no progress, you feel not only do you feel sometimes compelled, but you just have to. If you have at least
yeah. I
it's a
mean,
group solve. That's why not today. Kind of.
yeah. I mean, essentially, we're today group solving. I forgot the solution at some point. I had to kind of resolve it in my head, but yeah, I had freshly solved it, so I remembered. Okay, like yeah, I'm not gonna be lying that oh my God, this is an easy problem. I remember the solution completely. No, I don't. This is hard. Like this is
Were
very
there
tough.
any other solutions without holes for this problem?
I don't think so. I think Halls is okay. There actually might be. Like you can phrase it a bit differently. Like I don't know. There will be some kind of global thing that allows you to do this. Maybe I'm not sure. I didn't really look at all the solutions.
Maybe
The
like
ones I
the
saw.
inequalities which you can use Jensen's, but like some that one guy would have done it in AMGM by applying it like 20
Yeah,
times.
yeah, yeah.
Yeah, yeah.
Exactly. Oh, okay. We did a lot of things today.
And like, if this was actual piece of paper, I don't know how long this would be.
True. I think we can stop recording.
Yeah.
Oh, wait, what? Oh, I'm host. Oh my God. I
What?
didn't realize. I didn't realize I was the host of the meeting.